Next one is narrow interface for debugging trace, or NIDENT. Our marketing group doesn't like that name, but it kind of stuck, and so we're stuck with it. So basically what this is doing is we realize that going forward in fielded systems, we have problems. People are debugging more and more in closed-up fielded terminals. And so there isn't a 60-pin trace connector that you can easily connect to. And you're not putting that on a production phone anyway, because that connector we specified costs 10 bucks. So we have to find a way of somehow providing some visibility into the mobile terminals. And one of the ways we realized was that there are certain interfaces that are normally visible in a fielded terminal. And NIDENT is one way of addressing that. We'll talk about gigabit trace, and Sneak Peek also leveraged that, but in a different way. NIDENT is talking about leveraging that just at the pins. It means that we actually take the normal function that's connected to the pin and put another function on top of it. So we're not sharing protocol stacks in hardware, we're not sharing protocol stacks in software, we're actually physically remapping the pin. So NIDENT defines how to do that. It defines the pin mappings of a debug function over some other function in the chip, the true function of the interface. And it also defines how you switch the interface, because that's just as important. So if you're trying to connect, if you don't have a way of switching a functional interface to a debug interface without jumping through hoops, then the visibility that that interface might provide you is useless, because you can't actually get the interface switched over. So we're currently very close to releasing the V1.0 of the NIDENT specification to the board, and the focus of that one is remapping the micro SD interface that's pervasive but becoming less pervasive, unfortunately, in the mobile space. It focuses on remapping that interface to debug, and it supports trace and basic 1149.x debug. We're looking for new interfaces if possible, but as everybody knows, the number of interfaces on the mobile terminals is actually getting quite small. Audio connectors and memory is disappearing, so we're not sure where NIDENT goes in the future. So that moves us to gigabit trace and Sneak Peek. Now, in some ways they are like NIDENT, because the idea here is that we need to use functionally visible interfaces for debug in certain use cases, particularly debugging a fielded terminal. Where they differ from NIDENT is the fact that we're not changing the function of the pin or the protocol that runs on that pin. So we're actually using the interface as a functional client as opposed to stealing the interface itself. So in the case of gigabit trace, what we're doing is we're saying, okay, we have these network connections. That's usually what these functional interfaces are, right? We're talking about network connections. We're talking about things like USB that exist on the terminals today. It's a network connection. So for gigabit trace, we're going to export high bandwidth trace data over USB, or over gigabit Ethernet, or over something else that is available on the mobile terminal. And so it is just that, and it's gigabit trace. And Sneak Peek is a complement to that. This is where we're developing a protocol for actually interacting with the chip. So Sneak Peek is a sort of a DACS function, whereas gigabit trace is a DIVS function. And so Sneak Peek is, your sort of traditional stop mode, high intrusive debug. So it's important to note in these that the network connections are shared between debug and other functions, like I stated. Debug in this case is just another application layer client. We're not trying to circumvent any functions that might be sharing this same link with us. And the important thing here is we're doing this, and by doing this, this enables us to debug on fielded terminals without having any dedicated debug interface. And so, as part of this effort, we needed to make sure that the top-level protocols are completely independent. We're not a network independent. We're not, doing gigabit trace or sneak peek for any particular network. We're doing them for all networks that might come down the line. And then, but we're also going to provide you the information for gluing them to particular networks as we move along. And so as part of this effort, we're trying to, we had certain goals. The idea would be that we were trying to define the protocols so that it would be possible in steady state to have the data transfers be managed without any kind of on-chip or target system application threads managing the link or the network. So the idea would be that once you get gigabit trace set up, which might require some software help on the target system side, you don't have interrupts constantly firing to manage the transfer. That it doesn't have to be this way, but we wanted to make sure that the protocol enabled non-intrusive types of transfers like that. And then moving on, we have this generic layer, the network independent layers, but then obviously it's just as important to adapt those layers to specific networks, because there are things about networks that need to be thought about. And so we will be providing network-specific adapter documents that talk about things like transfer sizes and how handshakes work, and the other transfer-specific usage models. Some networks support multiple types of network traffic, streaming versus discrete transfers, and so which ones are we supporting for a particular function? I just want to mention this a little bit, that gigabit trace and sneak peek are not replacements for the legacy debug that might happen over a PTI or things like that. There are problems and careabouts and gotchas with this that don't make it suitable for all debug use cases. Okay. One of them is the fact that if you look at the networks that are available on field terminals today, they don't have the bandwidth of a traditional PTI that you might have literally dozens of pins. So, anybody that's done processor trace on a modern processor that's running 1.5 or 2 gigahertz knows that you can generate gigabits per second worth of data. So you're not going to get that off chip with the current network interfaces that are on the terminals. But you can still get valuable information. If you need to have super high bandwidth, you're going to have a very wide connector. So that means that the wide connector isn't necessarily going to go away. Other limitations that you have are that even if you can minimize the amount of on-chip software interaction that you have to have, there's still problems with things like gigabit trace, because, you can imagine, if you're trying, we have to share this interface, so if you're trying to do trace, high bandwidth processor trace whenever you're streaming video over the same USB, somebody's going to notice that things aren't what they're supposed to be. You're going to be dropping frames, and you're also not going to be you're not going to be getting the same amount of trace data that you would get over a dedicated link. And there's other functional issues, the bus hangs, power and reset problems, and misbehaving software in general can impact the data flow or just disrupt your system to a point where it's unusable. So it's not a perfect solution, but it is a better solution whenever you don't have any solution. So that's the message to take. But legacy debug will still be used. It has to be used, and because of some of the problems that I've stated. So I just wanted to frame that. I think it's really important. Maybe I got a little strident there, but okay. So a little bit of the details about gigabit trace. So we have, actually there's a sort of a forward reference here because I haven't talked about the trace wrapper protocol yet. But we have published a specification called the trace wrapper protocol that talks about how trace can be exported off a chip and gives you a bunch of primitives for doing that. Gigabit trace is just a formalization of how to use the trace wrapper protocol. Okay. Everybody knows that Derb is online.
just click it, it'll go away.
Does it? Okay.
There. Sorry.
Oh, that's completely thrown me off now. You edit that out, right, Marcia?
Yeah. I will.
So all the idea of gigabit trace is to just formalize how we use these TWP primitives in a network environment. Because when TWP was originally developed, it was more for, I mean, we knew that we would eventually be mapping this to networks, but we were looking at it more in a parallel trace interface as the bottom layer in a system for trace. And now with the network, so that's what gigabit trace is. Gigabit trace is, okay, we know how to do trace, but how do we get it to the network? In a way that makes sense and also aligns with what we've been doing previously. So this is sort of the data flow and sort of shows where the different pieces fit in. So you have these multiple trace sources, and MIPI doesn't care what those trace sources are. We don't specify any particular functional trace protocol. I think that's also important. We go as far as with the system trace protocol to provide you a generic protocol that has a lot of useful primitives, but we do not specify this is how processor trace looks. This is how software instrumentation looks. This is how any kind of particular function in trace would work. But what we do specify is, once you have all these, we specify a way through TWP of combining those all into a single data stream, because that's important. That's something that we can do in MIPI. And then, of course, then we go to this next layer where, okay, so I've got all this data merged for you, but I need to get it to the network. So this is where the partitioning is. So in this gigabit trace network client, which is a sort of a virtual box in this diagram, it plays in both worlds. It uses TWP primitives, and it tells you how to map those primitives into network packets that you would send over a particular network. Because they're not all the same. Some networks give you facilities for denoting high-level message boundaries, others don't. Some networks require fixed packet sizes for transfer, others don't. So these are the kind of things that will be handled in a particular network adapter specification. So, switching over to Sneak Peek, this is the complement to gigabit trace. Sneak Peek is not unidirectional, it's bidirectional, and it allows you to interact directly through memory mapped interfaces with any memory map debug function within the target system. It defines a command and response format for that interaction. And it also has a fixed and user-defined register spaces for the status and control of this link. Our roadmap for this includes some standardized Sneak Peek peripherals that are not defined in Sneak Peek 1.0. And one primary peripheral that we're looking on our roadmap is a scan-based peripheral, because we still have scan-based debug elements within a system. And Sneak Peek right now is about memory accesses. So we need to have a mapping that allows us to use those memory accesses to touch the scan-based elements within the target system, and that's what the scan peripheral will do. We're also considering a trace peripheral that may or may not look like gigabit trace. If it really is just gigabit trace, then this will go away. There's still some discussions in the work group about what trace within the context of Sneak Peek means. So, in a nutshell, Sneak Peek is all about memory and memory accesses. And so we're not actually talking about debug other than the fact that it allows the debugger to get to things that have memory interfaces on them. So our command responses will allow us to introduce bursts onto the chip, burst reads and writes onto the chip. They don't have to be bursts, but they can be bursts. We support multiple memory spaces for these transactions. We support different flavors of access qualifications, and we have a robust error handling and reporting scheme that's defined in this. But those errors are all about either the link, the protocol, or memory accesses. This error we don't actually say anything about a debug function within Sneak Peek, and you'll see that in the next slide. And so we have system accesses, but we also define a more simple command set for talking to Sneak Peek internal registers, this local configuration control that we have. And that's just slightly different than what we have for the system memory, but we chose to define them as separate command and response packets.